Dr. Nicholas Cross.
The world is becoming electrified, which means that batteries are everywhere. They've been in your phones and laptops for some time now. Many new cars are powered by them, and soon they may even be powering airplanes. But batteries have this little problem. They are difficult, if not impossible, to take apart, diagnose and repair any issues, and put back together again. Think about it. If you have a bad battery, no one says, "Oh yeah, let's take a look inside." They say, toss it in the trash and just get a new one. So as scientists, we need to be able to predict when batteries will fail and understand the mechanisms that cause that failure. In lithium-metal batteries, one form of failure is the formation of what are called dendrites. So dendrites are these little tendrils that reach out from the electrode, scavenging for lithium. But if they reach out too far, they will touch the opposite electrode and cause the battery to short circuit and maybe even catch fire. And our ability to predict when dendrites will form doesn't align well with the experimental data on when they actually do. So my job is to build numerical simulations to improve our ability to predict dendrite formation. And I have found that the key is in the solid electrolyte interphase, or SEI, which is this nanometer thin film, the size of just a few hundred atoms, that covers the battery electrode and slowly grows as the battery is used. And the SEI is dense, which means that lithium has a really hard time diffusing through it to get to the electrode surface. And this slow transport can cause dendrites. So I've found that if we include a growing SEI into our simulations, they can be significantly more accurate. But how we do so is important. There are ways that we can include it such that the model agrees well with the experimental data, but completely contradicts the published literature on how we have seen the SEI grow. So I'm working with my computational and experimental colleagues at Livermore and our university collaborators to build a model that both agrees well with the experimental data and aligns with how we have seen the SEI change over time. As a result, we are learning how to better engineer materials and better operate our batteries to control solid electrolyte interphase growth and prevent dendrites as a form of critical failure in the next generation of batteries. This will enable your electric planes, trains, and automobiles to go farther and charge faster, and fewer batteries will be thrown in the trash.